So hi everyone, I'm Kenzie. Like Catherine said, I'm a PhD candidate at UW-Madison for one more month. So I'm really excited to present some of my work on novel technologies for dairy manure treatment. I'm just gonna make this active. There we go. Cool. So usually I have to spend a decent amount of time convincing people to care about cow poop, but you all seem to like cow poop, so I'm among friends. So I'll keep this brief. Essentially, we have a lot of dairy manure, especially in Wisconsin, and this dairy manure has a really high concentration of nutrients, right? So one of the ways that we try to utilize those nutrients is maybe through direct land application, but because of the variable composition of dairy manure, it can be really challenging. A lot of times we apply in excess of agronomic need, which can then lead to downstream water quality impacts like eutrophication, harmful algal blooms, etc. So, if we're able to instead extract the nutrients from the dairy manure and recover it as like a pure fertilizer supplement, it would probably be a little bit easier to apply in accurate quantities and a lot easier to market, right? A lot easier to sell fertilizer than cow poop. But this begs the question, maybe, maybe, how are we going to do this extraction? So I'm going to present one technology, which is, this does not want to work today, bioelectrochemical systems for ammonia recovery from dairy manure. So, or BES for short. BES offer a manure treatment method that is going to treat the organic load of manure while removing pathogens from the final end product. And they're able to recover nutrients, and I focus mainly on nitrogen in a more pure, usable, marketable stream. So, a little bit of technical background on how you can understand how we do this process in bioelectrochemical systems. So to understand these, you really just need to know that there are three main parts. We have a biological anode that's connected through an electrical circuit to a chemical cathode. So the way that I like to remember it, biological, electrical, chemical, bioelectrochemical system. Don't we love it when scientists name things? Um, and then within this cell, we're going to have two main processes of importance. So the first process is the current production pathway. And during this pathway, microorganisms at the anode, nope, we got to go there. We'll figure it out, you guys. Microorganisms at the anode are going to degrade manure organics into products. And my research doesn't look too detailed at those exact products. Instead, we care about the production of extracellular electrons that happens when this degradation occurs. So the microorganisms are able to essentially eat the manure. I call it microbe sandwiches. And when they eat those sandwiches, they produce electrons that are sent to the cathode as current, where they're consumed with a reduction reaction. In our case, it's the oxygen reduction reaction. So that's our first pathway. Our second pathway is the nitrogen mineralization and recovery pathway. So in this pathway, microorganisms are also going to eat microbe sandwiches. In this case, though, the sandwiches have a lot of organic nitrogen in them. So our microbes are able to mineralize that organic nitrogen into ammonia, ammonium, which is beneficial because, and this is where our two pathways intersect, because we have this influx of negative charge into the cathode chamber, we're going to need to balance that with an influx of positive charge. So we call that the electromigratory force or the force of electromigration. And that is beneficial because we are mineralizing nitrogen to ammonium, which is positively charged ion. We can transport it, maybe, thank you. We can transport it across that membrane into the cathode, where it's converted to ammonia based on our high pH. And then it's very easily recovered via air stripping as ammonium sulfate, which is a direct fertilizer supplement. So two pathways, one for current production, one for ammonia transport and recovery, and they kind of intersect because this one is driven by this one. I will mention that what I've just described is the galvanic process. We call that the fuel cell operation mode. And we can also have an externally applied voltage across the electrodes, which is going to really just enhance that flow of electrons. It's going to increase the electromigratory force. And that would be what we called electrolysis cell mode. So in the data I'm going to show you, experiments C and D are electrolysis cell mode, and experiments E and G are in fuel cell mode. So with that, I get to share some cool data with you guys. So the good thing that we found is that this process works. It does recover nitrogen. And we saw that nitrogen removal is slightly enhanced in this electrolysis cell operation mode. So you can see that reflected in our total nitrogen removal efficiency. Electrolysis cell is going to be the bars. It's a little difficult to see. The bars to this is your left. It's a yellowish background. And we can see that we have a little bit higher total nitrogen removal efficiency than we do in fuel cell operation. We see the same trend reflected in this parameter called R sub n, or the nitrogen loading ratio. Now, this is just a measure of how efficiently the system partitions current to nitrogen transport. So it's a value measured in amount of nitrogen removed per amount of current produced. And we can see far and away, it's much higher in electrolysis cell operation, which makes a lot of sense, right? Because when we have electrolysis cell operation, we're applying that external voltage, so we're enhancing the electromigratory force, which is going to draw more ammonium across that membrane. The interesting thing that we found, though, is that the current producing organisms in the cell seem to favor fuel cell operation. So that's reflected in this parameter called CE, or Coulombic efficiency. So this is similar to that Rn parameter, except reverse it and make it for general organics. So it's a value in terms of amount of current produced per amount of organics removed. And we can see that the microbes are much more efficient, although it's low overall. Microbes are much more efficient at partitioning or at using degraded organics to produce current in fuel cell operation. And that's also reflected in our maximum recorded current density. It's much higher in fuel cell operation. This is really interesting to us. It's actually in contradiction to a lot of published studies where electrolysis cell enhances, or electrolysis operation enhances current production. My best guess for what's happening is we're electrocuting some of our microbes, which we really tried hard not to do. We did it nice and slow, but they still didn't like it. So definitely something we have to look into in the future. So with the last couple minutes here, I want to take some time to talk about what I like to call the future outlook for this technology, because I've just spent a lot of time telling you about some cool lab data, but ultimately we want this to be a technology that dairy farmers can use. And the questions that we're concerned with about as environmental engineers is, okay, if we scale this up and dairy farmers are to use it, is it sustainable on the large scale? So we were able to, with the help of some amazing collaborators, Becky and Horacio, especially Horacio, my LCA god, thank you. We were able to use some previous experimental results to serve as the basis for a scale up of this treatment scenario on a 700 plus animal unit dairy farm in Wisconsin. So the data that I'm going to present with you today, you can advance, thank you, is a partial LCA, and it has a functional unit of per ton of manure treated and an allocation of the massive milk that was produced. This kind of combined the best of both worlds for us. It combined, we care about the amount of manure that we're treating, but the dairy farmers are obviously, their main product is the massive milk that is produced. So we combined them in both functional unit and allocation. And we investigated three main scenarios. So we looked at the no processing scenario. We looked at a solids liquid separation manure processing scenario. And if you're unfamiliar, SLS is usually implemented to help recover some of that nutrient fraction of manure. So it served as a good basis for comparison for our technology, which recovers the nutrients. And then, of course, our MFC treatment technology. And the results are pretty promising. So we looked at first greenhouse gas emissions, and we saw that greenhouse gas emissions for the MFC treatment and for SLS are much better than the no processing scenario. And for MFC treatment, it's pretty much on par with this other nutrient recovery technology that we found. I will say, however, literally yesterday, we discovered that there was an error in our assumptions that is really going to change this number and make it a little bit lower. We're not sure how much lower yet. So I don't have the data to share with you about that yet, but definitely something that we are investigating. But it is very interesting, right, to think about how just one assumption can change the output from this model. And so that'll definitely be something we need to consider when we're making recommendations for scale up. We also looked at ammonia losses, and this is where our treatment technology really shines. We have much less ammonia losses for the MFC treatment than both the no processing and the solids liquid separation treatment scenario, which makes sense, right? We're recovering that ammonia. And so if we're recovering it and using it as fertilizer, we can't lose it. The thing that, oh, one too far. One more. Perfect. The thing that I want to mention here is that we had a system boundary of cradle to farm gate. So we were looking at assuming that the ammonium sulfate would be applied externally from our farm. So we're not accounting for any ammonia losses that happen after that application because we stop at the farm gate. So again, goes to show how we need a little bit of investigation into the different assumptions. And then the last thing that I'll share, thank you, is we also looked at the eutrophication potential of this technology. Again, much better than the no processing scenario and slightly better than solids liquid separation. I'm really interested in delving a little bit deeper into what goes into this number. I'm not an LCA expert and I'm not totally familiar with all the different aspects that go into eutrophication potential. My assumption is that the reason that this is still quite large or not necessarily that much better than SLS is because we use a lot of freshwater dilution. And so it'll be interesting to investigate some like water reuse and reclamation scenarios towards scale up. So with that, I'll just end by saying that BES offer a up-and-coming sustainable option for manure management that can help improve water quality. So we're able to treat our dairy manure, or hopefully any manure, and recover this direct fertilizer supplement product that can be more easily dosed to fields and more easily marketed, which will hopefully lead to some happier fishes. We have some smiling fishes here. And then for my last little slide, I just have to say a huge thank you to everyone who's helped me with this work, especially my advisor, Mohan Jin, Horatio, and Becky for being so helpful and teaching me literally everything, answering all my questions. My amazing undergraduates, and I'm happy to take any questions. I also have to plug myself. I am graduating and I just got a job, so I'm looking to establish some collaboration. So if you're interested, both my emails are there. I'm